Um, in this video for CS360, we will cover the language pair of states trick. So this is a trick for showing that a language is regular when the language is constructed out of another regular language. This is only one of several examples and tricks that were covered in lecture 6 of the notes for how to show languages are regular. So you should check out that lecture for other details. But this one trick is particularly useful, and we will illustrate the trick by giving an example. So suppose A is regular, so let A be regular, and then let's say we have a language defined in terms of A, and in particular, let C be the language of all x, y, such that yx is in A. Okay, so here x and y are just to be clear, are strings in sigma star. Okay, so show C is regular. So here we constructed C out of A. A is regular, and we want to show C is regular. And then, so one trick, one way of doing this that sometimes helps is what I call the language pair of states trick. So the first part of the trick is step one is we need a DFA for A. Now we know there exists one, so let's use some notation to denote it. So let's just say that hold on a second. Oops. Okay. So okay, so let's just say that let m so let m be a DFA for A. So like that recognizes A. So because A is regular, we know that this exists, right? So in particular, we know the language of M is exactly equal to A. Okay, so we have such a DFA. And then we define the languages A, PQ. So these are languages. So this is the language of all strings X in sigma star, such that basically delta star of P X equals Q. So this means this notation, recall that the delta star is the extended transition function. It tells us where we would go from state P after reading all the symbols in the string X. Okay, so we're applying delta multiple times, one per symbol in X. And then, so this condition, delta star Px equals Q, says that if we start from state P in the machine M, and then we read the string X, then we get to state Q. And the language APQ is the language of all strings that cause the DFA M to move from P to Q. Okay, so if the DFA M were to start at P is not necessarily the start state, but suppose the DFA M is already at state P, then the language APQ is all the strings that cause the DFA to then reach Q, okay, when it reads that string. So this is well defined for any pair PQ. So APQ is a language. So we APQ is a subset of sigma star. It's a language over sigma for all or for any P and Q in Q, for any states, any pair of states PQ of M. Okay, so this is step 2 is to define these. Okay, so they're already defined in the notes. So if you're using it in an assignment, you don't need to redefine them. And then step 3 is basically to construct C out of APQ, out of the language's APQ. So we have many APQs, of course. So we want to represent C in terms of the language's APQ. The language's APQ are going to be regular. Why are they regular? Well, because there's basically, it's a very simple modification for M will recognize them. So all we need to do is modify M so that its start state is now going to be P, and its only accept state is going to be Q. And once we make this modification to M, then suddenly M accepts a string if and only if it causes M to move from P to Q, and therefore M accepts a string if and only if it's in APQ. So this modification of M is a DFA for APQ. So APQ is therefore regular for any P and Q. Okay, so if we construct C out of APQ using kind of standard operations that preserve regularity, then this will be a proof that C is regular. Okay, because we know that all the APQ languages are regular. And some operations we're allowed to use is concatenation, union, star, intersection, so we're allowed to use any such operations, and we're trying to build C. We're allowed to only use finitely many operations, though. Right? Remember, infinite unions or infinite intersections don't preserve regularity. Only finite unions or finite intersections, finite concatenations, only things like that preserve regularity. Of course, the star operation also preserves regularity. Okay, so then let's just quickly do this for C. How would we construct C? So, let's just write again. So what is C here? C is, right, so how do we construct C? So we want to kind of think of C as concatenation of two components, right? An X piece and a Y piece, such that YX is an A. Okay, so basically, first let's think of all the strings in A and how they can be decomposed into a concatenation of two pieces, right? So for A to be decomposed into two pieces, then we can think of where M goes when it sees Y. So this is basically delta M of Y, where M ends up when it sees Y. This is basically delta star of Q0 comma Y, right? This is where M ends up when it reads Y. And then we can kind of go from there. And take another delta star from there, reading X. Okay, so we can read Y, get to some state delta star of Q0 Y. And then we can read X and get to another state, and we want this to be in F, right? So this condition is equivalent to saying that YX is in A, because M recognizes A. So right, like YX is in, is in L of M. Okay, so this condition here is equivalent to saying YX is in L of M. We can, if we call this state P, okay, then we're basically saying, that Y is going to be a string in a Q0P for some P, okay, and then let's call let's call this this other string over here Q. So Q is in F. So then X is going to be in a PQ. Okay, and then Q is going to be in F. Okay, so basically what we're saying is that A can be written as the union over P in Q, states P in Q and states Q in F of the concatenation of y and x. So basically, this is a q0p, concatenate a p q. Okay, so A can be written like this. A can be written as this union of concatenated pieces. Okay, basically because anything in A can be split into two pieces in any way you want. The first piece lets you reach state P, and then the second goes from P to Q, and Q has to be something in the accept state. Okay, and then from here, it's kind of easy to see how to construct the state C of all xy instead of all yx. Okay, so that's C is going to be the union over P in Q and Q in F of A PQ A Q0P. Okay, so this is going to be the state, the language C. Now notice that the union is only over finitely many things. There's finitely many P's in Q and finitely many Q's in F. So there's finitely many such pairs. So there's a finite union, and concatenation of a pair of regular languages is regular. So each concatenation here is regular. The finite union is also of regular languages. The finite union of regular languages is regular. Therefore, C is regular. Okay, so this is sort of a proof that C is regular. Of course, what's missing in this proof is actually proving this equality. So this equality, we've kind of vaguely hand waved. We said, okay, that sounds like it might be true. One would need to formally prove this, right? So one would need to show that any string, if W is in C, then W is in that union, right? It is in this union. And then when we need to show that if W is in the union, then W is in C. So you need to show both directions. And I believe the notes go through the proof of this. So I won't go through it in the video. So the point is just that you should remember this trick of considering these languages prepare states, languages A, P, Q, and how you might decompose various languages that were made out of A, that were constructed out of A, how you might construct them through the languages APQ. For example, here, we did it this way, right? So and the languages APQ we know are regular, and so therefore any kind of regular operations that you apply to them will still give you regular languages. And that's a convenient way of showing the language is regular. In this case, we showed C is regular. Of course, if you're using this on an assignment, don't forget to actually prove the equality. Don't forget to prove that C really is equal to the union, or whatever else you're claiming that C is equal to. So that does require proof. Okay, so this is just a good trick to know about dealing with regular languages.